All right, welcome to 9.6, the ratio and root tests. These are the last two tests to test for convergence or divergence of series. So the first one we're going to look at is the ratio test. And we would tend to use the ratio test when factorials and or exponentials are involved. Okay, so what is the ratio test? Well, we would take the limit as n goes to infinity of the absolute value of an plus 1 over an. Okay, now remember, so if it's an alternating series, we could go ahead and just look at the absolute value, forget about the alternating portion. Okay, if it's less than 1, it converges absolutely. If that limit is greater than 1, it diverges. If it equals 1, it's inconclusive and we have to use a different test. Okay, so let's look at this first example and see how the ratio test works. All right, okay, so this first one, we have the series from 1 to infinity of 3 to the n over n factorial. So I see exponential and I see factorials. So this is a good idea to use the ratio test, especially because of the factorial portion. So remember, we are going to look at the limit as n goes to infinity of the absolute value of an plus 1 times, I can think about it as times 1 over an, right? Or an plus 1 over an. So really we're taking the reciprocal of this guy. That's 1 over an. So what does this look like? Well, wherever I see an n, we replace it with n plus 1. So it becomes the limit as n goes to infinity of 3 to the n plus 1 over n plus 1 factorial. That's our an plus 1 term, times the reciprocal of this, n factorial over 3 to the n. And now we just have to use our algebra to clean this up. So 3n plus 1 becomes 3 to the n times 3, all right, and then n factorial. N plus 1 factorial, we could rewrite it as n plus 1 times n factorial, and then we have the 3 to the n. So the 3 to the n's cancel, the n factorials cancel, and we are simply left with the limit as n goes to infinity of the absolute value of 3 over n plus 1. Well, when we substitute infinity, we get 3 over infinity, which goes to 0. Since 0 is less than 1, we can make our conclusion that this converges absolutely by the ratio test. Okay, let's take a look at this next example. All right, so as we're looking at our series, all right, again, I notice a factorial. So this is really good for the ratio test. Whenever there's factorials, ratio test is our go-to, okay? Sometimes exponentials as well, but our root test will be saved for those. Okay, so we're looking at the limit as n goes to infinity of the absolute value of an plus 1 times 1 over an. All right, so again, wherever I see an n, I replace it with n plus 1. So we have the limit as n goes to infinity of the absolute value of n plus 1 to the n plus 1 over n plus 1 factorial. And now we take the reciprocal of the original, n factorial over n to the n. Breaking things up, n plus 1 to the n plus 1 is n plus 1 times n plus 1 to the n. N plus 1 factorial is n plus 1 times n factorial. So again, our n factorials are going to cancel. Our n plus 1s will cancel as well. So what are we left with? We are left with the limit as n goes to infinity of the absolute value of n plus 1 to the n over n to the n. Now, since they're both raised to the n power, we can go ahead and rewrite this. Okay, so we can rewrite it as one quantity raised to the nth power, and now splitting up this n plus 1 over n over n becomes 1 plus 1 over n to the n power. Now, if we use our direct substitution, we're going to be left with a 1 to infinity scenario. So remember, this is where we set equal to y and then ln both sides. Okay. So as we go through, we're going to go ahead and set this equal to y, and then we're going to take the ln of both sides, moving that n power in front. Now, this is a scenario where it's infinity times infinity, so we have to move and reciprocate. So I'm going to move the n to the denominator, and it's going to become 1 over n because we have to reciprocate. All right. So at this point, we can also go ahead and forget about the absolute value bars. It's not going to be relevant at this stage. Okay. So now we need to we need to use L'Hopital. Okay, because we're going to get 0 over 0 scenario. Okay, so when we take the derivative of the top of our numerator, we're going to get 1 over 1 plus 1 over n, and then we have to remember about the chain rule. So that's going to lead us to times negative n to the negative 2. Okay. And then our denominator, 1 over n, that's like saying n to the negative 1. So taking the derivative, negative n to the negative 2. So now we can say that those guys cancel, and we are strictly left with the limit as n goes to infinity of 1 over 1 plus 1 to the n. Now when we substitute 1 over 1 plus 1 over infinity, well, this guy goes to 0, so this just goes to 1. So we can solve for y. So we can say, oh, well, y is equal to e, right? Getting y by itself, e is greater than 1, so this diverges by the ratio test. Now, one thing to keep in mind, and as a shortcut, I want you guys to recognize this portion right up here, and it's right here, okay? I want you guys to be able to recognize that the limit as n approaches infinity of 1 plus 1 over n to the n power really is e. So if we see this at any point, we can go ahead and make a conclusion right away at this stage here that y equals e. Okay, and we'd be done. So we're skipping out on all of this. All right, saves us a bunch of time to recognize this right here, that's just e. Okay. All right, now if you remember a while ago, we kind of talked about how that is e. But yes, if we can recognize that, we can save ourselves some time. Okay. All right, I want you might be able to see part of the answer to that third one, but I want you to try the third example here, set up the ratio test, and see if it converges or diverges. So pause the video, give yourself a second, a little bit of time, try it out, and then see how it goes. All right, let's see how we did. So remember, we want to think, okay, I have this alternating series, right? So we're thinking nth term test. But we would get it to be inconclusive, all right? It would equal 0 as we take the limit, okay? So we have to set up our ratio test, okay? And let's see what we get. So again, remember, since we're dealing with the absolute value, I can essentially omit the alternating portion. We're just looking at the positive portion when we set up our ratio test, okay? So we're going to take the limit as n goes to infinity of n plus 1 squared plus 4 over 2 to the n plus 1, and then times the reciprocal of an, 1 over an. All right, so multiplying n plus 1 squared and then adding 4 to that, we get n squared plus 2n plus 5. 2 to the n plus 1 becomes 2 to the n times 2. All right, and now we can kind of cancel some things. We should see the 2 to the n's. Those cancel, and then we can distribute that denominator. 2 times n squared times 4. So our numerator becomes n squared plus 2n plus 5, and the denominator becomes 2n squared plus 8. As we take the limit of that, we'll have to use L'Hopital a couple times. Okay, so just kind of note, yeah, we are using L'Hopital in there, but eventually we get down to just the coefficients, 1 over 2. 1/2 is less than 1, so this converges absolutely by the ratio test. Okay, let's take a look at the next page so we can look at what the root test entails. Okay, so the root test, I only have one example that goes along with this, but the root test is used when the ratio test doesn't work. Okay, so if we're dealing with factorials, typically the ratio test. If we're not, we can throw the nth or the root test in there. So what does the root test say? Again, we're looking at the absolute value of the series, okay? And what we're going to do is we're going to look at the limit as n goes to infinity of the nth root of that sequence, of that an. So another way we could write this is the limit as n goes to infinity of the absolute value of an raised to the 1 over n power, okay? And that's going to equal some value. So if L is less than 1, then the series converges absolutely, okay? If it's greater than 1, it's going to diverge. And if it equals 1, it's inconclusive. So the same results apply for the ratio test as the root test. Okay, so less than 1 converges absolutely, greater than 1 we diverge, equals 1 we're inconclusive. All right, so let's take a look at this one and only example. So notice here I don't have any factorials, so the nth root or the ratio, the root test is going to be a good idea to use, or potentially a good idea. Okay, so we're going to look at the limit as n goes to infinity of the absolute value of that series raised to the 1 over n. Okay, so that's the limit as n goes to infinity. I can drop the absolute value bars at this time because it's not an alternating series. So it's 2 to the 3n plus 1 over n to the n, all raised to the 1 over n power. So now what we can do is we can distribute this 1 over n to each of those guys. So power of a power, we multiply. Okay, so 3n times 1 over n becomes 3. 1 times 1 over n becomes 1 over n. So it's now 2 to the 3 plus 1 over n. This is the entire power. N to the n, well, this n times the power of 1 over n just becomes n in the denominator. So it makes things a lot easier. And now when we plug infinity in, right, we get 2 to the third plus 0. So 2 to the third is 8. The denominator becomes infinity. So 8 over infinity just gets us to 0. 0 is less than 1. So we can say that by the root test, this series converges absolutely, right? So again, the root test is used typically when there are not factorials. When there's factorials involved, we want to use that ratio test, okay? And we'll go from there. All right, if you have any questions, let me know.